Pretty good. Good? Yeah.
Perfect.
I know, right?
The best part is that my voice is going to be on YouTube now.
Alright, so do that.
Yes.
I think about Russian dolls when I see a problem like this. You guys know what I mean when I say that?
Yes.
Little dolls that fit inside each other. I had to make it a little bit more equal by making it a prodigal style, right?
It's just like cheating on it.
Yeah, exactly. So the easy one is the first part of the prodigal. Let's say take rid of that guy, leave this guy alone. Well, that's nice. Plus, now leave that guy alone. Derivative of this guy. So the really funny thing is, the first thing you do is you actually sort of apply a partial derivative to this. Because you take the derivative of sine of something as if this something was just x or something, right? It's the first thing you do. You don't even pay attention to what's in here. So you're treating it like partial with respect to this. That's what's kind of funny. So the derivative of sine of something is cosine of that thing. And then you start to make your chains.
X squared.
Yeah, now what's the derivative of the inside?
X squared.
Oops. And if actually, to make this a little bit easier, this is natural log of 3x and negative 2, if that makes it any easier. Right. So the derivative of natural log of something is
1 over.
1 over that thing
So it's just
times
like 2x over. My bad. 3 over 2x.
So the derivative of the inside, be careful, you're not taking the derivative of this. I think that's what's happening. You're taking the derivative of the inside, which is this. So the derivative of that is just going to be negative 6x to the negative 3. Cool. And of course now if you cancel a couple x's out, cancel some numbers out, what do you do? Right? The cleanup should be easy. It's getting there that's difficult. Right? And I can, right there I can see the problems that crop up. We look at the wrong thing at the wrong time. We look at this instead of looking at where we're supposed to be looking at. Right? That's why very often I'll try to tell students, the way I teach this is of course, the prodigal piece is easy enough. And then I'll try to say, okay, now x, start here, times the derivative of the inside. And now focus your attention on that. Natural log, do the derivative times the derivative of the inside. So you force yourself to write, so the next step would be 1 over that times the derivative of the inside. So then you're focusing your attention on what derivative you're interested in right then. At this point, most of us should be able to do this in one fell swoop. Right? So here's the connection to what we're doing. And let me give you something a little bit freaky first, just to make sure everybody understood what I said partway through this. Anybody know what the derivative of this would be?
Negative.
What's that? Square root minus 1.
Do you guys see with this notation? What's this mean? D by dx, sine x. What's that? Yeah, so what is it? Cosine. But that's because that matches with that. That's why it's easy. So shouldn't this one be easy too? This is derivative with respect to x squared minus 1. Cosine of? Do I have to do more? No, good. I'm not doing that on purpose to freak people out, but that's really what I meant when I said that. That's where that first piece came from. We took the derivative of this as if it was sine of the thing we're taking the derivative with respect to. But this was really with respect to x. That's why I had this other extra pieces at the end. Cool. And one little last thing I want to make sure you guys know, and maybe were told before, if y equals x, let's see. Sure, well, x squared. What's dy dx? 2x. Officially, it's 2x times the derivative of the inside. I don't know if you guys really know. And the only reason here it doesn't show up is because that, of course, is 1. Right? This is going to become very important a little bit later when we make a better chain rule. Right? That's going to come a little later. Okay. So I just needed to make sure that you guys remembered all the little ins and outs of chain rule with one variable, because now we're going to be talking about chain rule with multiple variables. Yeah. So let's say I have this here.
It's cold.
Yeah.
You see, do I want to go ahead? Yes. Cool.
Which is x and y.
Now see, how does this relate to our regular chain rule? Our regular chain rule, before you had this, by itself, right? Something like that. The variables are kind of shifting around there a little bit, but that's basically what we had. We had some function of x where the inside was a function of something itself. That's the idea of chain rule. We have some inside function. So here I've got two possible inputs to play with. So we're going to play both of them. I say, okay, both of them are functions of something. How many truly independent variables are up here then? Truly independent. So what does z depend on? X and y. It directly depends on x and y. So obviously z is not dependent. What do x and y depend on? So how many truly independent variables? Okay, so let's start there. There's one truly independent variable. There is one, what we call, there really is one official dependent variable. Dependent? So this was here, this one truly is t. One truly dependent variable is z. X and y we call the intermediate variables. They're the go-betweens, right? I don't have a function explicitly in t, but I could if I plug t, if I replace this in there, put that in there, then I have a function of t. Two intermediate variables, x and y. Okay, so that's step number one, is to realize that. So now, how in the world do I figure out then dz dt? Let me actually ask you also at the same time, anybody know why I didn't really write that as partial z, partial t?
You don't have to?
I love it. Why not?
considered z as a function of t, it's only one variable.
Yeah, z is a function of only t, right? So where do partials, where are they really needed? Why does that name partial make total sense? No pun intended. Well, why does partial make sense?
When we have two independent.
If I have a function of more than one variable, if I only do with respect to x, that's only part of what I could do. I could also do this. Here, what more could I do? So what partials could I write with z, possibly? It's this here, right? So what partials could I write with z? Exactly. I could do partial z with respect to x, partial z with respect to y. Do you guys see why those are necessary? Because there are two different things I could hold constant. There are two different things I can look at as being the true variable there. Whereas if I wrote it as a function of t alone, I don't need a partial. That's the only thing I could do. That's it. Okay. So really here, this is a funny little thing that no book ever really directly talks about. Is this really wrong to write then? Is that really incorrect to write? Let me give you a concrete example. If I have f of x equals x squared like we did earlier, what's the partial of f with respect to x?
2x.
Was there really any, now you guys had a little trepidation there because you're still getting used to partials, a lot of you, but was there really any difference between what's the derivative of f with respect to x? Derivative of f with respect to x, what's that?
2.
Aren't these the same stupid thing, right? Is this necessary here? No. And technically, very often it's considered wrong, but me personally, I'm like, that's a more general way to write it, to cover your ass in case there's just something else you didn't see or something, right? This is the partial. If there is nothing else, what else is there to hold constant? Nothing. Does it change the work? No. Okay, maybe. But in this book and in this class, we will write this if it's understood that z is a function of only one variable. Whereas if I do it with respect to intermediate variables, there's two of those bad boys. That's why it's got to be partials then. Okay, how are we doing there? Cool. Where am I? Okay. So what the hell would this thing be then? I don't want to lose that. Recall, if you had, let me see how I'm going to write that. H of g of x. If you had this, wouldn't this be, to do the dy dx, I don't know if you guys remember seeing this notation before, this would be dh dg times dg dx. Does that look at all familiar? Your professor might have used a u there or something else, I don't know, right? So if you want to say y equals h of u, then y dy dx, or dy du, sorry, would be dh, what do I want to say? Oh, h of u of x. Now you make me change my whole notation. Du dx. Does that look at all familiar? That's the chain rule in action. That's what the chain rule looks like in general form. That's the general form chain rule. And that's what I said earlier. This is why I said this earlier. When you do that first step on chain rule, you are taking the derivative with respect to that whole damn thing inside. The first step on derivative of cosine of x squared minus 1 is do the derivative of cosine. You get negative sine of blah, right? You're doing it with respect to the thing inside. So that's the beautiful thing up here. What I'm going to do here is, with one variable here, with one intermediate variable, really, I've only got to have one of these things here. dh, du, du, dx. And your professor probably pointed out that these look like they cancel, don't they? And wouldn't that be what I really want? Derivative of h with respect to x, right? So up here, how do I get dz dt? Well, what could I do z with respect to? We said it just a minute ago. I could do d partial of z with respect to x. Now, how do I write the next step? It's going to have a dx here.
Partial of x.
And do they have to be partials? Because x is only a function of one variable. It's only a function of c. I love it. Would you really be wrong if you put partials there? Not really, but in a way you would be, because you only write the partials when you really need to. And the way I look at it is actually, you can write this when it's okay to do so, when there really is just one variable. I like to think of it the other way. Partials are more general. We're allowed to write it with a true D if there really is just that one variable. There's only that one option, right? Now, am I done with this? No, I'm not done with this. There's more. Shit. What's the other way to get dz dt?
dz dy.
Partial of z with respect to y, dy dt. That's the difference. Here, of course, there's only one of them, and we're getting used to this. A lot of the work is the same, except we've got more parts to it because we've got more parts to everything in this class, right? There's more parts everywhere. So here, this would have been good enough before with no weird d's, but now we've got two of these bad boys because we have two intermediate variables, x and y. And what do you get really? I like to think about it like this. These two kind of cancel. And if z is in the x and the y, if I put the part with the x together with a part with the y, I get the whole dz dt, don't I? Aren't these both basically like dz dt? Yeah. It's the part of dz dt in the x piece plus the part of dz dt in the y piece together to make the whole damn dz dt. I'm tired of saying dz dt. Okay, I'm hoping to God that you guys kind of get this. It's kind of nice. What do you guys think then? Try to write this. Try to write, let me bring back our infamous W. If I had W equals some function of x, y, z, where x is a function of t, y is a function of t, and z is a function of there, t. What is dw dt? Write that down. What do you guys get for this?
Partial W, partial.
Yeah, partial W doesn't matter, right?
Partial
So let's say partial of f for W. There's that cool. Partial of f with respect to x dx dt plus. What's up? Everybody all right? What's up? Partial of f with respect to y dy dt plus dz dt. Cool. Okay. All right. Not too bad. So I can extend that to however many dimensions I really feel like it. It's just going to be more stuff there. You do all the parts. You've got to get all the parts put together before you can get the whole thing. So you got to figure out what are all the parts that I have to put together to make this do. Okay. Cool. I'm trying to pull this up so I can show you something up here. Yeah.
Quick question. So I'm gonna do all this work I'll be asked to find a derivative of that work. If I just need one partial of that,
I like it. Cool.
then I'm just gonna.
So this is dw dt. If they ask you what's the partial of w with respect to x, then you just take the partial of w with respect to x. That's that one thing they're asking for, right? Cool.
Would I use again the general there, like just that one section?
Well, it depends on what this function is, really, right?
Oh, I see. Okay.
Cool. So let's do a concrete example now that we've kind of talked about how to set it up. Let's do a concrete example of one of these. And then I want to show you visually what's going on with this thing. So say we have plus 20. So first find that. Find at what points is the change in z 0? So 2 steps there. So I see it's really important to write the form down first and then figure out the pieces you need to throw into the form. So make sure everybody starts in the right place. How would you do dz dt in this case?
You could plug it in.
Good, because you can do z with the x piece. Partial z with respect to y. Dy dt. I like it. And all those derivatives are pretty damn easy to do. You just got to put them all together. Alright, so let's see. Now to put this thing together. Well, if you guys got part B, it's not too bad after you get this one, maybe. What's dz, partial z with respect to x? 2x. Right? Because everything else is thought of as a constant. So the rest of it, this negative 3y squared plus 20, is a constant. It goes away. Partial of x with respect to t. I like it. So x is 2 cosine t, so it'll be negative 2 sine t. Cool. Partial z with respect to y. Negative 6y. And then dy dt. 2 cosine t. So if you throw all that stuff together, dz dt, so it'll be 2x times negative 2 sine t, so it'll be negative 4x sine t, right? And it'll be negative 6y times 2 cosine t, so it'll be minus 12y cosine t. How are we doing there? Is that right? Throwing all that stuff back together? Now, I can clean this up a little bit, and some of you guys might realize we're still kind of, believe it or not, we're still in the easy part of this. That's why some of you guys might realize there's an easier way to do this problem, because the functions we're using are not horrendous yet. Couldn't I just throw these stupid things in here and take the derivative with respect to t directly? Right? And it's the same things that don't mean a damn thing because we have to figure out how these things work before we hit the ugly shit. Right? So we just assume that we don't realize we can do that. And we start attacking it this way. What can I do now, though, that kind of relates to what we just said? What is x? 2 cosine t. And y is 2 sine t. So then I get...
You get negative 16 sine 2t.
Yeah, so you get... where is the negative sign at? I lost the negative somewhere. Oh, yeah, yeah, because it's a negative. Yeah. Lost the negative somewhere. Oh, no, that's right. It's negative 32 cosine t. Oh, yeah, yeah, I see. And of course, here, 2 cosine t sine t is sine 2t, so then you get, that's where you get your negative 16 sine or cosine. Cool. Oops. Sorry. Sine 2t. Okay, cool. You see that cosine sine identity popping up in a lot of places. So now part B should be relatively easy then. I'm asking you at what points is the change in z 0? Like if you moved at all, if you changed t at all, z wouldn't really change. It's really like in a way it's a horizontal tangent line. In this case, it'd actually be a horizontal tangent plane. We'll worry about that for section 11 or 12.7. So how do you do this? How do you figure this out? Yeah, set the derivative equal to 0. So you need sine 2t to equal 0. And where does it happen?
0 pi over 2 pi.
Yeah, so basically any integer multiple of pi over 2. Right? 0 pi over 2, pi, 3 pi over 2, all those kind of things, right? So it'll be like n pi over 2, or k pi over 2 if you like k. So let me show you the picture, the actual graph of this thing. Don't worry, I got to get this up here first. There he goes. All right, sweet. Oh, let's see. Oops. Not that one. No. Oh, David.
They don't have everything you know specific. Why is this Native American? Why is this Native?
Ah, here. Cool.
That's an N.
Oh, yeah.
All right, guys. So the graph of this is one of these guys. I remember this guy here. This was not the easiest thing in the world to draw. What am I doing, guys? When I have x equal 2 cosine t, y equal 2 sine t, what shape does that trace out?
Circle.
Circle. It shapes out a circle in the xy plane. So what I'm really doing is I'm saying if I follow this with all my inputs, if I put all my inputs to this, will follow this path. Right? They have to be a part of this path here. And really what I'm doing here then is I'm saying as I move around this path, as I move around this circle, what's happening to my outputs? How quickly is it going up or down? That's what dz dt is. Right? So as I move around this circle, and I think I'm actually able to sort of move around the circle. Yes, here we go. That kind of shows me at that point. So what did we figure out? We figured out, in part B, we figured out where the change is 0. Now just visually, where is the change going to be 0? Where, like here, is is it changing a lot right there? Yeah, that's big time change. In fact, that's probably going to be like the maximum place where it's going to be changing. There's probably something related to an inflection point on that side. You see that? You just kind of chop it right there. You can look at it. There's an inflection point because then it starts to go cup up from cup down up here. So there are 0 locations here. And of course, you can see that. So let t equal. Let's see if I can force it to be there. I want more control. Too bad for me.
You just click it.
I want 0. You jackass.
What's that little? What's the little back arrow thing? Is that all the way?
No, this is going to play like that. Yeehaw! Woohoo!
Yeah.
Yeah.
So late.
Now it's become like a reaction time gauge, and mine was really bad. But at least I want you to hopefully see that there's the math of what's going on. The visual of what's going on is really kind of cool. If I'm walking on this terrain that's just up and down, but somebody's like looking from above, I've got a torch. I've got I got a fire on the end of a stick, right? I got a torch, and they're looking down at me. And if I'm walking, like I'm going up and down like crazy around this stupid, but I'm making a circle. So from above, it just looks like a freaking circle, right? Me, I'm going crazy up and down, up and down. That's what this dz dt is trying to say. It says to keep in that circle, how quickly do I have to go up or down? Well, at this point, I'm having a good time. Like, oh my god, oh shit. Now I've got to go way back up to keep them going in the circle. You guys kind of see what I'm saying? I'm not sure exactly why this guy's walking around with a torch. But it's a good visual, I think, to have. All right. Yeah, that's why. I like that. Don't give guys with one acid fire. Okay. Oh. Oh yeah, we're gonna get a break. I know it's a new thing. Here's something a little bit interesting. Let me see if I can get I want you to notice something about this. Let me pull that x over, make it look a little more like a function of x equals 0. Right? So make it look like more like a z equals something. So if I pull that x over here, now let's try to implicitly differentiate this bad boy. What we're actually going to do, I said this wrong earlier, top of my head I couldn't remember the name of it, but we're going to create something, a little bit easier approach to finding implicitly the derivative with respect to x, y, dy dx. Right? So there's a nicer approach to that. So how does implicit differentiation work? How